Today we will be conducting the Coco Collision simulation from Lesson 3 of MyStars Unit 7.3 in order to investigate the question, how does temperature change? In this system, there are many more air molecules than Coco molecules. In the Coco Collisions system, there are 20 air molecule cards and 12 Coco molecule cards. Coco molecules are moving fast and thus have lots of energy. This is why the Coco molecule cards have a larger number written on them. If you added up all the energy on the cards, you would get 117. Air molecules are moving slow and thus have less energy. This is why the air molecule cards have smaller numbers written on them. If you added up all the energy of the air, you would only get 55. Since the air molecules and Coco molecules are constantly moving around, we will periodically shuffle the Coco Collision cards. We also have a collision zone on the Coco Collisions board. This is where the air and Coco meet and is the only place energy is transferred in the system. It is like the cocoa is in a well-insulated mug. You're probably wondering why there are blank boxes in each of the molecule cards. In the Coco Collision simulation, there will be multiple rounds of collisions. Therefore, these empty boxes are for us to keep track of how the energy within each of the molecules changes throughout the simulation. Now we can start the Coco Collisions simulation. For each round of the simulation, there are 4 collisions. To make things easier, let's zoom in. Starting with the first set of molecule cards, we first add up all the energy and then evenly divide it between the 2 molecules. The sum of energy between these 2 molecules is 10. Because the molecules leave the collision with the same amount of energy, both the air and Coco molecules end up with an energy of 5. And these values are written in the first empty boxes on the molecule cards. We can also calculate how much energy each molecule card gained or lost during the collision. Because the air molecule went from an energy of 2 to an energy of 5, it gained 3. Since the Coco went from an energy of 8 to an energy of 5, it lost 3. Now we move on to the second collision. The sum of the energy between the 2 molecules is 15. Because 15 cannot be evenly divided between the 2 molecules, we'll give an extra energy to the molecule that came into the collision with less energy. This keeps the math simple. For this collision, the Coco leaves with an energy of 7, and the air molecule leaves with the collision with an energy of 7 plus 1 extra, which is 8. Just as before, these values are written in the first empty box on the molecule cards. During this collision, the air molecule gained 5 while the Coco lost 5. On to the third collision. The sum of Coco and air molecule energy is 14. Therefore, each leaves the collision with an energy of 7. In this collision, the air gained 3 while the Coco lost 3. For the final collision of this round, the sum of the energy is once again 15. And just as before, 15 is not easily divided between the 2 molecules, so the air molecule leaves the collision with 8 because it started the collision with the lowest amount of energy, and the Coco leaves with 7. In this final collision, the air molecule gained 6 while the Coco lost 6. What did these collisions and energy transfers do to the energy of the Coco and the air? To find out, we calculate how the energy changed within each molecule after the collision. From the first collision, the air molecule gained 3, so we write plus 3 in the gain-loss cell. During this same collision, the Coco molecule lost 3, so we write minus 3 in the gain-loss cell. From the second collision, the air molecule gained 5, so we write plus 5 in the gain-loss cell. And the Coco molecule lost 5, so we write minus 5 in the gain-loss cell. We continue this process to see that the third collision air gained 3, while the Coco lost 3. And the last collision, the air gained 6, while the Coco lost 6. Now we have all the gains and losses of the individual molecules. We can calculate how the total kinetic energy of these 2 systems changed. There are a few ways we can do this. We could add up all the energy values on the molecule cards, or we could add or subtract the gains and losses for each molecule card from the total kinetic energy. We'll go with adding and subtracting the gains and losses because it will be faster than having to add up all the molecule cards after every round of Coco collisions. Prior to the collision, the air as a system, that is energy from all the air molecules, added up was 55. In contrast, the total kinetic energy of the Coco started at 117. We can now add and subtract all the gains and losses from the starting total kinetic energy to see how the total kinetic energy changed. We start by adding or subtracting the first gain-loss from the total kinetic energy values. We see that the air started with 55 but gained 3 after the first collision, which brought the total kinetic energy to 58, while the Coco started with 117 but lost 3 after the first collision, which brought its total kinetic energy to 114. If we continue this process of adding and subtracting the gains and losses from the total kinetic energy, we see that by the end of the first round, the air has a total kinetic energy of 72 and the cocoa has a total kinetic energy of 100. Be sure that you fill out all the gains and losses and total kinetic energy values in your table. Now that we have added all the gains and losses to the total kinetic energy, we can calculate the average kinetic energy for all the air molecules and all the cocoa molecules. This is done by dividing the total kinetic energy by the number of molecule cards. For the cocoa molecules, we divide the total kinetic energy after round 1, which is 100, by the number of cocoa molecule cards, which is 12. This means that after round 1, the average kinetic energy of the cocoa is 8.33. We could do the same for the air molecules. The total kinetic energy, 72, divided by the number of air molecule cards, 20, is equal to the average kinetic energy of 3.60. Now that we've completed the first round of cocoa collisions, it's time to move on to round 2. We'll first collect all the air and cocoa molecules and shuffle them really well to account for the fact that molecules are constantly moving around. We then lay out the molecule cards into 4 columns, just as we did at the beginning of the simulation. Once again, we'll start the round by moving each pair of air and cocoa molecules into the collision zone to calculate their change in energy. To speed up the process, we'll skip some of the details from the first round. A quick note before we get started. Notice that even after shuffling the cards, one of the air molecules from the previous round ended up in the collision zone again. It is okay that this happens. The first set of air and cocoa molecules enter the collision zone and the sum of their energy is 13. So the air receives 7 while the cocoa receives 6. These values are written into the empty boxes. We also see that the air gained 2 energy while the cocoa lost 2. For the second collision, the sum of the energy is 11, so the air molecule gets 6 and the cocoa gets 5. In this collision, the air gained 4 while the cocoa lost 4. In the third collision, the sum of the energy is 14, so both molecules leave the collision with 7. Once again, the air gained 4 and the cocoa lost 4. And in the final collision, the sum of the energy is 15, so the air gets 8 and the cocoa gets 7. In this collision, the air gained 1 and the cocoa lost 1. Just as before, we'll enter the gains and losses into our table. Here are all the gains and losses entered for the air and cocoa molecules after this round of collisions. If we add and subtract these gains and losses from the total kinetic energy, we see that the air ended round 2 with a total kinetic energy of 83, while the cocoa ended the round with a total kinetic energy of 89. Be sure that you fill out all the gains and losses and total kinetic energy values in your table. Also, it will be up to you to calculate the average kinetic energy in the cocoa and air molecules. Now we'll move on to the third round of cocoa collisions. Just as before, we'll collect all the cards and shuffle them really well to account for the molecular movement. We'll then lay them out into the 4 columns and move the 4 pairs of air and cocoa molecules into the collision zone. In this round, a cocoa molecule that was already in a collision ended up in the collision zone again. It is okay that this happened. The sum of the energy from the first air and cocoa molecules is 8. Therefore, each leaves the collision with an energy of 4. For the second collision, the sum of the energy is 12, so each molecule leaves the collision with an energy of 6. In the third collision, the sum of the energy is once again 8, and both molecules leave the collision with 4. And in the final collision, the sum of the energy is 18, so both the air and cocoa molecules leave with 9. Just as before, we'll enter the gains and losses into our table. If we add and subtract these gains and losses from the total kinetic energy, we see that the air ended round 3 with a total kinetic energy of 97, while the cocoa ended the round with a total of 75. Be sure to fill out all the gains, losses, and total kinetic energy values in your table. Also, it will be up to you to calculate the average kinetic energy in the cocoa and air molecules. Now we'll move on to the fourth round of cocoa collisions. Just as before, we'll collect all the cards and shuffle them really well to account for the molecules' movement. We'll then lay them out into the 4 columns and move the 4 pairs of air and cocoa molecules into the collision zone. In this round, 3 cocoa molecules and 1 air molecule that were already in previous collisions ended up in the collision zone again. It is okay that this happened. The sum of the energy from the first air and cocoa molecules is 9. Therefore, the air receives 5 and the cocoa receives 4. For the second collision, the sum of the energy is 11. so the air gets 6 and the cocoa gets 5. In the third collision, the sum of the energy is 12, and both molecules leave the collision with 6. And in the final collision, the sum of the energy is 10, so both the air and cocoa molecules leave with 5. Just as before, we'll enter the gains and losses into our table. If we add and subtract these gains and losses from the total kinetic energy, we see that the air ended round 4 with a total kinetic energy of 101, while the cocoa ended the round with a total of 71. Be sure that you fill out all the gains, losses, and total kinetic energy values in your table. Also, it will be up to you to calculate the average kinetic energy in the cocoa and air molecules. Now we are on to the final round of cocoa collisions. Just as before, we'll collect all the cards and shuffle them really well to account for the molecule's movement. We'll then lay them all out into the 4 columns, and move the 4 pairs of air and cocoa molecules into the collision zone. The sum of the energy from the first air and cocoa molecules collision is 11. In this collision, the cocoa started with lower energy, therefore it receives 6 while the air receives 5. Since we ran out of boxes for the air molecule card, we'll just write the new energy value here. For the second collision, the sum of the energy is 15, so the air gets 8 and the cocoa gets 7. In the third collision, the sum of the energy is 6, and both molecules leave the collision with 3. And in the final collision, the sum of the energy is 9, so the air receives 5 while the cocoa receives 4. Just as before, we'll enter the gains and losses into our table. If we add and subtract these gains and losses from the total kinetic energy, we see that the air ended round 5 with a total kinetic energy of 105, while the cocoa ended the round with a total of 67. Be sure that you fill out all the gains, losses, and total kinetic energy values in your table. Also, it will be up to you to calculate the average kinetic energy in the cocoa and air molecules. We've now completed the cocoa collisions simulation. Let's take a look at the final results. Here we can see all the gains, losses, and total kinetic energy values from each of the collisions from the simulation filled out in your datasheets. Make sure that what you wrote down matches what is in these tables. On your own, you use the equations in the average kinetic energy columns to calculate the average kinetic energy of all the air and cocoa molecules after each round of cocoa collisions. You'll then make a series of graphs that will help you complete this activity.